Okay, welcome back to Physics 1, and today we're going to be talking about centripetal acceleration and centripetal motion. So what exactly is centripetal acceleration or centripetal motion? Well, if you look at a circle or something driving in a circle, what you'll see is that it follows some kind of curved path, obviously, because it's going in a circle, and typically, with centripetal acceleration and centripetal motion, a lot of people suspect maybe acceleration is pointing in some tangential direction or something along those lines, or some people even suspect that the centripetal acceleration is pointing outside of the circle, something along these lines. And unfortunately, this is not a correct description of centripetal acceleration, centripetal motion, and how you use it. So essentially, if you have this circle with some radius defined as r, you can accurately find the acceleration of some particle moving in a circle like that. So how do you accelerate in that circle? Well, the centripetal acceleration vector will always point towards the center of the circle. So if this is the center of the circle, this is some radius r, that centripetal acceleration vector always points this way if that's the particle. Always, no matter where it is along that curved path, it will always point towards the center. And if, for instance, you are driving and you go over a hump or something like that, even if you're on that hump, that centripetal acceleration vector will always point towards the center of that curve or circle. So what's the importance of centripetal acceleration and centripetal motion? Well, if you're for any reason interested in rockets or design of rockets, a lot of times we're talking about orbital mechanics, and the very basics of orbital mechanics has in some rocket particle orbiting something in some kind of circular motion. Now, in real life, there is the same principles do apply, but you won't have perfect circles. You will have some kind of elliptical shapes. Something like this is what an actual orbit would look like. And so this is where it actually does come into effect. But you still use the same exact principles. So let's talk about the force then. So what exactly, if there's some kind of acceleration towards that center of the circle like that, what would be the force some particle that's moving along that path would experience? And conveniently enough, the force is just mass times velocity squared divided by the radius. And we'll talk a little bit more about the derivation of this and where it comes from shortly. But let's talk about a common misconception, which is something called the centrifugal force, which is a fictitious force. It doesn't actually exist in the inertial reference frame. It's an experienced force by a topic called the Coriolis acceleration and rotating reference frame. So if you're not standing, so if you're in some kind of circular path, you feel some kind of acceleration pointing out. But if you look at the person that's actually in the circular motion, you don't see this kind of, you don't feel this exact force. What you see is them moving in a circle. And this is more for an advanced kind of undergraduate course, typically something called dynamics or even physics mechanics or math physics is where you would see something like this. So the derivation of the centrifugal force, the fictitious centrifugal force, isn't really too necessary for this, but just know that there is no vector that points outside the vector of the centripetal motion. Centripetal acceleration points to the center of the circle. So, where does this mv squared over r come from? Well, in upper division dynamics classes, what you come to learn is that this is actually from a type of coordinate system called the NTB coordinate system, which is the normal tangential binormal coordinate system. And essentially in 2 dimensions, it's just the normal and the tangential coordinate system, or the normal and tangential vectors, which is just if some particle is moving along some kind of weird path like this, at any given point along this path, this particle has a tangential acceleration and a normal acceleration. And same thing for velocity. It has in both components, and that defines its motion along this curved path. So when you look in the dynamics textbook, what you'll come to see is that the normal acceleration is derived as being the velocity squared divided by rho, where the rho is the radius of curvature. And the tangential acceleration is just defined as the acceleration in some positive direction along the tangential path. Now, the radius of curvature, where does it come from? Where does this r come from? So if you're talking about some kind of elliptical spheroid or some kind of weird looking path or something like that, and you're looking for the radius of curvature at any given point, you can use this funny formula to be able to find it. Again, Physics 1, you're not going to see it, but just know that this is something that you can use if you're interested in actually finding genuine like elliptical orbits or some kind of thing along those lines. So, now back to Physics 1. How do we use it? We're using Cartesian. So, essentially what you're going to have to do is if you ever have some kind of object moving in a circular pattern, you're always going to want to set up your coordinate axis system to be in the same frame as the normal tangential coordinates axis. So you're always going to have y or x pointing towards the center of the circle, so that way you don't have to do any kind of funky angles to solve for the actual acceleration in the centripetal direction. So you'll always have, so no matter what the path looks like, you'll always have something pointing towards the center of the circle. That way you always keep your centripetal acceleration positive and don't have to do any weird angles for it. So let's do some practice. Let's say you're on a roller coaster like this. You're driving along, and you go up this loop, and you come back around. What is the speed, so we're talking about just the magnitude, that is needed to keep the passengers in their seat at the top of the loop, so up here? So, what does it mean, top of the loop? Or what does it mean by to keep the passenger in their seat at the top of the loop? Well, if we draw a Fourier diagram of this cart as it's at the top there, we see that this thing has gravity, and the exact same direction also has a normal force, right? Because if we look at some person sitting in this seat, they are sitting like this, they're upside down, they're having some fun like that. They're still, well, very lightly, they still have a normal force that is pointing on them in the same direction as the gravitational force. So what we see is we have two forces pointing in the same direction, and now we need to define that coordinate axis system. So I'm going to define just positive y going this way. We'll say positive x is going that way. Positive y should be the only thing we actually need for this question. So I'll do the same here, y, x. Now we can write a sums of forces equation. So we'll do sums of forces in the y. We have n plus mg is equal to mass times acceleration centripetal direction, which is just the same thing as saying n plus mg is equal to, remember we said earlier, mv squared over r. Now we have that radius of curvature, is they defined as r. We don't know the normal force, but we can solve for, and we don't know the velocity. But what does it mean for just barely keep them in their seat? To just barely keep them in their seat. It means that as they come around this loop, this n is so little. It is 0.0000000 to infinity 1. So small, but it's just there, which means that they're just staying in their seat. But anything so close to 0 is essentially 0 for our intensive purposes. So we can solve for this velocity by saying that anything faster, right, than this velocity, there's a normal force greater than 0. Anything less than this velocity, there is a normal force less than 0. So we say n is equal to 0, and we say we have mg is equal to mv squared over r. And again, this velocity, if it's greater than this v calculate, we'll see VLC. If it's greater than VLC, so if the velocity of this thing is greater than that, they will have normal force. They'll have some positive normal force greater than 0. If v calculated, or if the velocity that this thing is going is less than v calculated, then the normal force will be less than 0, which means they are falling out of their seat. So that's essentially what we're doing, is we're saying n equals 0, and we see just barely how fast does it have to be for them to go around this circle so that they stay in their seat. Well, we multiply by r, we also can actually cancel out these m's, so we just have rg is equal to v calc squared. Now we can square root this, equal to v calc, and there's your answer. The square root of rg. That's how fast they have to be going in order to stay in their seat. Let's talk about this airplane. So we have an airplane here that's climbing in a circular path. We want to find the normal force the passenger feels, and we're given some velocity and some rho and some radius of curvature. So let's define again our coordinate axis system. So remember, always we need something pointing in the same direction because we're essentially adopting the NTB coordinate system. So we always need something pointing in the same direction as the center of the circle and something pointing tangential to that. And we'll go ahead and write our free body diagram. We have our acceleration, centripetal acceleration, going in this direction. We have gravity pointing straight down, and we also have the normal force pointing straight up as well. Well, sorry, we don't have an acceleration. We don't have a centripetal because that is an induced force. So we just have the normal force pointing straight up, just like that. But we have the acceleration pointing in that direction. So let's go ahead and write our free body diagram. So we have this, something like that, and we'll give this some angle as well here. So this is some angle theta, and we have yeah, because this is like it's climbing out at some typically like 15-degree angle or so, 11-degree angle. So we'll say that this is the same angle there. So we'll write our sums of forces equation. So sums of forces in the y, we have n minus mg cosine theta, right? Because this is that side there. Mg cosine theta. And we have to say this is equal to mv squared over rho, right? Because that's what we just said. Now sums of forces in the x direction. We don't actually need it for this question, so we'll negate it for now. Because all it's asking for is the normal force, and we have all the variables here. So we'll say the normal force is equal to mg cosine theta plus mv squared over rho. We can actually take out the m's. We have n is equal to mg cosine theta plus v squared over rho, and that would be your final expression. All right, thank you for this centripetal motion video, and I will see you in the next one.